Swayam Prabha. Digital India. Educated India.
Till now, in the torsional vibration, we have studied simple by Newton's second law, how to obtain the equation of motion. Also, we have dealt with the transfer matrix method for multi-degree of freedom system. In these cases, all the rotors which we considered, generally the shaft of such rotors had only the stiffness property. Thus, we neglected the mass of the shaft. But in practical rotors, we find that not only the stiffness, also the mass of the mass or the inertia property of the shaft is distributed throughout the length. So, these shafts are very heavy, and because of that, they have appreciable amount of polar moment of inertia, and that is distributed throughout the length. So, in such rotors, generally when we want to model using discrete mass analysis, the analysis is not that much accurate, and for such cases we have approach that is called continuous system approach. Generally, we deal with such system with continuous system approach, and today we will see very briefly this particular approach, how to obtain the governing equation for the torsional case when the both mass and elastic property of the shaft is distributed. And our main focus would be in the subsequent lectures to have finite element formulation of such system, so that it can be applied to a real system. So, let us see what are the things we will be covering today. So, basically we will be developing the torsional vibration analysis using continuous approach, and we will introduce some basic terminology of the finite element method. In this free and forced vibration is the main analysis which we do, and some of the concepts like eigenvalue, which is nothing but natural frequency, eigenfunction. In discrete system it was nothing but the mode shape. Some other property like orthogonality property we will see, which is there for the eigenfunction, especially for the continuous system. Then some basic definitions which generally we use in the finite element method, like elements, nodes, field variable, degree of freedom of node and element. These are the basic definitions we will be introducing in this particular lecture, and in subsequent lecture we will be dealing with the finite element method in more detail. So, let us see how this particular continuous system approach works, and for this let us see what are the type of shafts we have considered. So, earlier we had one flexible shaft, especially for transverse vibration it is more clear. So, I am trying to explain this continuous system approach by transverse vibration, and subsequent then we will be analyzing. So, this is a massless flexible shaft and a heavy disc we placed, and such rotors we analyzed by considering only the flexibility of the shaft and the mass of the shaft. In another case we took rigid shaft and flexible bearing. In this particular case, the shaft we considered as rigid, only the flexibility was there in the bearing. But in some cases the rotors are relatively heavy, and flexible. So when we mount them on bearings, they not only have appreciable amount of inertia, also they have elasticity. For such rotors, we cannot able to distinguish where a particular mass we should able to concentrate at one location or several locations. So generally in this particular case, we will see that elastic property and the mass property of the shaft we need to consider continuously. This was the example given for the transverse vibration, in which we are interested in this kind of vibration. But the present study, we are interested in the torsional vibration of such rotor system. So let us see how this can be modeled. So for this particular case, if we have a shaft which is let us say this is the axis of the shaft Z, and this is the one of the plane of the shaft shown here, and at a distance Z, let us say there is a plane, the motion of that we want to analyze. In this particular shafts, we have various kind of loading, like we can have distributed torque, external torque acting. So that torque will be representing as function of Z, the axial position of the shaft. Also it is time dependent. And if we have some kind of concentrated torque at some location, which is let us say at location Z0, that is the location of that is fixed. So this will call as a concentrated torque. Now we are interested in a shaft segment which is here. So if we want to see that particular plane of the shaft due to this torsion, so let us say this is y and this is x axis. This is basically center of the shaft, so this will come like this. And if we want to study motion of the point P, let us say the coordinate of that is x, y, z. If we have angular twist of this particular plane phi z, which is again function of z and time, this particular point P will have displacement in the radial direction, which will come at P prime location due to angular displacement. And in this particular hypothesis, we are assuming that whatever the loading is applied on this torque, because of this, if one particular plane which we are considering, that will remain a plane, it will not distort during the motion, and a particular particle on this particular plane like P moves in that particular plane. So you can able to see that in this plane itself it is moving, it is not going out of this plane. Now if we want to analyze the torque balance for a particular shaft segment, let us say we are taking a very small shaft segment having thickness dz, and if we want to draw the free body diagram of that to obtain the equation of motion of this, let us take this particular shaft segment, and this particular shaft segment, as we have seen, the thickness is dz, and once we have taken out from the shaft, the reaction torques will be acting on both sides of this particular plane. So let us say in this particular direction, the torque Tz is acting, which is reactive torque, which is coming from the other end of the shaft. And we have, because inertia property is continuously changing, so we expect that the torque will change at other plane, and this will be given by this expression. Even the displacements, angular displacement, I am representing that, let us say positive direction is this one, phi z, which is function of z and t, and this direction also, because from left to right is the positive direction for the z. So here we have the displacement as phi z plus d phi z, change in the angular displacement. Because of this inertia property, there will be change in this particular angular displacement also. So now these two are the torque which are coming on this particular, these are the two torques which are coming onto this particular shaft segment. And now using Newton's law, second law, we can able to obtain the governing equation, and for that we will be equating the torques. So I will take in the next slide. So Tz plus delta t, this is the torque which is acting on the right side of that shaft segment, minus the shaft segment torque and the left plane, and that should be equal to the inertia, rotary inertia of the shaft segment. This now in this, because from torsion theory we know that T by J is equal to G theta by L, so we can able to get the torque as Gj, and this theta is the twist of the shaft segment, which is this, for this particular case is this much, and the length of the shaft segment is dx. So you can able to dz. So you can able to see in the previous slide, the relative twist of the two planes is difference of this angular displacement minus this, so that is the d phi z, and the shaft segment length is dz. So we got this one, and the IP, which is mass polar moment of inertia, is given as r square dm. Dm is the mass of the shaft segment, so we can able to write this as r square rho dv. So this is the mass, and then this we can able to write it as area, and dz, and rho we can take outside, and this can be simplified as rho dz, because dz will come out r square dA, and r square dA is nothing but the j, second moment of inertia, that is polar moment of inertia of the shaft, which is given as j as pi by 32 d4 for circular shaft. So this expression and this expression we can able to substitute in this governing equation. In this governing equation you can able to see that these two terms are getting cancelled, and here we will substitute torque, and here we will substitute IP. So d by dz, or for torque we will write Gj, and this for the torque, and d. So again you can see we have substituted for torque and this one, and right side we need to substitute for IP. So rho j dz and phi double dots. So this is double dot is representing the time derivative with respect to time derivative, and this is a double dot means a double derivative with respect to time. So you can able to see that this will get cancelled, and we will left with equation of motion of the continuous shaft for the torsional vibration, which will be given as like this. So this is the equation of motion of the continuous system. In this particular case, we did not consider the external torque, but if we want to consider external torque in the previous slide, here the we will be having external torques. So you can able to see that if we want to consider the external torque, here we will be having distributed external torque and concentrated torque, which was at the location of the Z0. So we will be using a direct delta function delta to specify that particular torque. So you can able to see this direct delta function is having property that when we have this will be equal to 1 when we have z is equal to z0, and this will be 0 when z is not equal to z0. So you can able to see that when we are specifying the z is equal to z0, then only this will act, otherwise it will not act, because this is a concentrated load and this is the external load which is distributed over certain length that will be specified. We have obtained the equation of motion of a continuous shaft for its torsional vibration. We have seen that this particular equation of motion is partial differential equation. It is having derivative with respect to z, the spatial derivative, and as well as derivative with respect to time. And this particular equation of motion represent because till now we have not considered any boundary condition. So if we consider boundary condition, the solution of this particular differential equation, which we will be calling as boundary value problem, will be unique. So let us take very simple example of a cantilever shaft. For that we will solve this particular differential equation, and this particular equation is having similar form which generally we study in the mathematics. There is we call it as a wave equation. So this equation is exactly same in form as wave equation, only thing is the variables are different. So now let us see, we will solve this particular wave differential equation for the boundary condition of the cantilever beam. So we have one shaft is having cantilever condition. You can able to see this is the z axis, length of the shaft is L, and it is undergoing torsional vibration. In this particular case, you can able to see that at the fixed end, the boundary condition is that this particular displacement, which is function of time and z at z is equal to 0, this displacement is 0 at this fixed end. On the other hand, this free end, there is no torque, and we have represented torque earlier like this. So at z is equal to L, we have the condition that torque is 0 because this is a free end. Now to solve the differential equation which we had obtained earlier, that is I am writing again, phi z is equal to dj Ez dz. We will be using the separation of variable method to solve this, and in this method we assume the solution in such that we have two parts of the solution. One function is purely spatial coordinate dependent, that is z, another is time dependent, and this time dependent function is generally harmonic in nature, and the form of this particular function, harmonic function, we know is cos omega n of t plus b sin omega n of t, where omega is a frequency, t is time, a and b are constants, and a and b we will be obtaining based on the initial condition of the problem. From the initial conditions we will be obtaining these two constants. Now, if we take let us, because in this particular equation we can able to see that we need to take time derivative of this particular function and also the spatial derivative here, and so now I want to differentiate this twice with respect to time. So obviously this will not derivate this chi function, only it will derivate the eta function which is time dependent, and if I want to differentiate this with respect to z, so that will go into the chi. I am representing that as prime to represent the derivative, partial derivative with respect to z, and this will be as it is. So these two we can able to substitute in the equation of motion, and if we substitute this in equation of motion, we will in the previous equation here, so we will get rho j eta double dot this chi z. So this is in the left side is equal to, in the right side we have, because this particular shaft we have considered uniform, so Gj will be constant, so it will come out. So we will be having Gj and double derivative of that function, so we will be getting chi double derivative with respect to z and eta t. Now if we see the harmonic function is having property, this particular, if we take double derivative of this with respect to time, basically we will get a relation as this. This is the condition of the harmonic motion, and if we substitute this here, we will get rho j minus omega square nf and chi z eta t is equal to Gj chi. So you can able to see that this chi will be common and it will be get cancelled. So we will left with a differential equation which is now only function of z. That means this is now ordinary differential equation. You could able to convert the partial differential equation to ordinary differential equation. So this will be having the form of this. And here this j will also get cancelled, and this we can able to write it as chi t by del square plus, I am calling that constant as alpha square, chi t is equal to 0, where alpha square is, as we can able to see here, is rho omega square nf by capital G. G is the modulus of rigidity. Now, this particular differential equation, which is now ordinary differential equation, we can have the solution of this. Sorry, this is only z, function of z, not function of time. So, the solution of this will be of this form: C constant cos alpha t alpha z plus d sin alpha z. So, this is the solution which we are assuming of this differential equation, where C and D are constant, and that will be obtaining from the boundary condition of the problem. And for a cantilever case which we are dealing with, we have seen that these are the two boundary conditions. So, from these two boundary conditions we will be obtaining the C and D value. So, let us see the first condition, that at z is equal to 0, this displacement is 0. So, we will get this as 1 plus d into 0. So, you can able to see that we are getting C is equal to 0 from first boundary condition, this fixed end boundary condition. Second boundary condition we have is this torque is 0. Because eta here in place of phi z, we are writing the assumed solution, this solution, and because there is a differentiation with respect to z, so this will be differentiated, this will be outside this one. So, this is 0. So, that means we need to derivate this with respect to z first, and we need to substitute here. So, we can able to remove this quantity. Also, this will not be 0. So, I am differentiating this, and we know that C is 0 itself. So, only we need to differentiate this d alpha cos this. So, this is the derivative of this particular term, and at z is equal to 0, z is equal to L, this quantity is 0. So, if we substitute d alpha cos, instead of z we will write L is equal to 0. So, you can able to see either d, if it is 0, then the whole motion will be 0, because C is already 0. If d is 0, motion will not take place. We are not interested in that. So, d cannot be 0. So, for that case, this alpha in general cannot be 0. So, we need to have a function, this cos alpha L is equal to 0. So, this is the frequency equation. This is the frequency equation, and the root of this will give us the eigenvalues, and from there we can able to obtain the natural frequencies. So, you can able to see the solution of this alpha L is equal to pi I by 2, where I can be odd numbers, and we have infinite number of solutions. So, infinite number of eigenvalues are possible, and earlier we have related alpha with the natural frequency of the system by this relation. So, we can able to get the natural frequency from this, that will be as I pi by 2L. So, after simplification we can able to get the natural frequency from these two expression like this, and here I is again varying from 1, 2, 3, 5. So, these are the various natural frequency of the cantilever shaft. Now the eigenfunction, the assumed solution, we had C is equal to 0. So eigenfunction is left nothing but psi chi is equal to sin alpha z. That again we can able to, and here some constant we can able to attach, and alpha is already given there. So this will be pi I z by 2L. So this will be the eigenfunction, and eigenfunction will give us how the relative points in the whole shaft will be having displacements, because in this particular case each and every particle point on the shaft will be having relative displacement with respect to each other. This function will give us the relative displacements of various particles in the shaft system. Continuous system approach, as we obtain the natural frequency and the eigenfunction which represent the mode shape. In continuous system, because the mass property is continuously distributed, so basically this system can be considered as an infinite number of degree of freedom, because each and every particle are independently moving with respect to each other, and we have seen that we are getting infinite number of natural frequencies because we have infinite degree of freedom in the continuous system approach. So now whatever the eigenfunction we obtain, let us see the plot of that for first three modes. So this is the plot of the eigenfunction. So you can able to see this is the position of the shaft, this is the fixed end of the shaft, and this is the free end of the shaft, and this is the angular displacement, and this is a relative angular displacement. So we have taken the maximum displacement as unity, which is for this particular case for first mode. So this is belonging to the first natural frequency corresponding to I is equal to 1. So this is the first mode, and for second natural frequency the mode shape will look like this. This is the fixed end. Maximum is taking place here and here also, here plus minus and here minus 1. This we are normalized because this is a relative displacement. So the maximum we are taking as 1, but here you can able to see that if we draw the 0 line, there is a one place where the shaft displacements are 0. So and either end of this particular shaft is having opposite angular displacements. So this particular position is called node, as we have seen earlier also. So there will not be any angular displacement of the shaft at this particular place, but either side of this two will be having opposite motion. Again I am repeating, we are talking about the torsional angular displacement. So the shaft at shaft particles which are left side and right side, they will be having opposite motion. Similarly, this is the third one is for third natural frequency, and here if we draw the 0 line, we will see that there will be two nodes where there will not be any angular displacements, but there will be angular displacement in either side, and this two will be having opposite motion and this two will be having opposite motion. So, and we can able to plot this for higher natural frequencies also, and we expect for such cases additional nodes will be coming as we will increase the natural frequencies. For the continuous system approach, we have obtained the natural frequency and mode shape for one particular boundary condition. This was cantilever case. In continuous system approach, we can able to obtain this natural frequencies for simple boundary conditions, and few more boundary conditions solutions I am providing here. So, like we have, if free shaft is there is no support at both ends, then the natural frequency will be given by this expression. Here the eigenfunction will be having this function, sine function, and for another case in which both the end of the shaft is fixed, in this particular case natural frequency will be given by this, and the mode shape will be like this, is also sine function, but there is some difference. This is the fixed free case, this is fixed case, and this is free. So, this is fixed free, this is similar to the cantilever, this is a cantilever case, this is fixed and this is free, and these are the natural frequency and mode shape. So, basically we need to satisfy the boundary conditions to get the constant, that C and D, and depending upon that we can able to get the this equations. Once we obtain the eigenfunction for a particular disturbance, if you are talking about free vibration, if you are giving a disturbance to the system, how the system will vibrate will be given by the expansion theorem, in which we mention that any free vibration we can able to express in terms of these eigenfunction, contribution from these basic eigenfunctions, and contribution of various eigenfunction will depend upon the initial condition. So, let us see this particular torsional free vibration, how we can able to express in terms of the eigenfunction. So, this is for the case for the simply support for the case of the cantilever beam case. So, this was the eigenfunction, and this is the harmonic function. So, you can able to see that we are expressing any general free vibration in summation of various eigenfunction and the harmonic function, where A and B is the contribution of various modes, and this will depend upon how we are giving the initial conditions. And for zero initial condition like this, if our initial conditions is not zero initial condition, at time t is equal to 0, for initial condition t is equal to 0, if we have these angular displacement and angular velocity, these constants we can able to get by this. Basically, to get this we need to multiply both sides of this equation by the eigenfunction for one particular mode, and we need to integrate over the domain. And while integrating, we will be using the orthogonality of the mode shape. That means, when these two mode shapes are same, when they are not same, then this is 0 and this should be equal to. So, when they are same, then it will not be 0. So, when two eigenfunctions are same, this quantity will not be 0, and when these two eigenfunctions are different, then this will be 0. So, you can able to see that once we are applying multiplying by in both sides by eigenfunction of the ith mode, the terms here will be 0 corresponding to all modes except I, and that is the case here. So, these have been obtained using the this orthogonality condition of the mode shapes. So, you can able to see for different initial conditions we can able to get these constants, and the free vibration can be described. We have analyzed the torsional vibration. The analysis for the axial vibration for continuous system is exactly similar to the torsional vibration. Only thing is some of the variables we need to interchange. So, for axial vibration, so if we are talking about a shaft having axial vibration, that means longitudinal vibration. So, if you want to analyze this system, we need to replace the angular displacement which we took in the torsional vibration by axial vibration, that is a linear vibration, and the J second moment of area, the polar moment of area, we need to replace with A, G we need to replace with E, and torque we need to replace by force. So these will be the changes in the equation of motion, and otherwise the analysis is exactly same. Differential equation, eigenfunction, everything is same, only we need to replace these variables, then we can able to analyze the axial vibration. So we will not be repeating the axial vibration analysis here, but just we are trying to show the analogy here. In the continuous system approach, as I mentioned, for more complex boundary condition or for multiple disk or multiple support, the obtaining solutions are not easy. I will just show one particular case in which the same cantilever beam in which we have this shaft is having continuously distributed stiffness and mass property, but along with that there is a concentrated disk at the free end, and this addition of the disk, how the complexity increases because of this, we will try to see. So we have in this particular case a cantilever shaft having distributed mass and stiffness property, and there is a concentrated disk at the end. Let us say the polar moment of inertia of that is IP. So in this particular case, we can able to see the boundary conditions. This particular disk either we can take in the boundary condition. So fixed end, the boundary condition is same, that is this is at z is equal to 0 is 0. Here to obtain boundary condition, let us take the free body diagram of the disk. So in this particular case, if this is the positive direction for the angular displacement, there will be reactive torque from the shaft onto this, that will be acting, and that will be this at z is equal to L. So from this we can able to get the boundary condition here. That means if we take the equation of motion of this, because this particular torque is acting in the negative direction, this is the only torque acting on this particular disk, should be equal to this is at z is equal to L, should be equal to inertia. This is the polar moment of inertia of the disk, and phi is at z is equal to L. Because this disk location is at z is equal to L, this angular displacement, which is basically in general representing the displacement, angular displacement of the whole shaft at any location of the z. So we need to specify that this angular displacement which we are talking about for this disk is at z is equal to L. So this is the equation which we obtain, is the boundary condition of the problem. Earlier, because there was no disk, so right hand side was 0, but because there is a disk, this is having right hand side which is this. Now let us see how this boundary condition gives the complexity in the solution. So we had the equation like this, in which C and D we need to obtain with the boundary condition. So for this boundary condition, we, because this phi z we chose as multiplication of the this and the time function. So in this particular case, time function is not there, so basically we can able to write this as, so I am satisfying here. So xi at 0 eta t at this is at z is equal to 0 is 0. So, you can see eta t c plus d into 0. So, this we already seen that for this particular case, because eta cannot be 0, c, this gives the c is equal to 0. This was the similar condition as the previous one. The complexity is there in the second boundary condition now. So, now we need to substitute here the solution. So, I am taking this in the second slide. The boundary condition I am rewriting. Like this, and because we have the harmonic function eta, so we can able to write so basically here if we substitute this here, we will get negative of that, we will get negative of this. So, they will get cancelled. Now, we will satisfy the boundary condition. So, you can able to see that if we take the first derivative of this, because c is already 0. So, this will be similar to the previous one. We have substituted for z is equal to L is equal to so here also we have substituted for this. So, we can able to see that now this equation we can able to simplify as tan alpha L is equal to rho g L by I p 1 by alpha L. So, with some rearrangement we can able to write this equation like this. So, here you can able to see that the solution of this is not easy, because we need to solve for alpha, which is here also. So, this is a transcendental equation. So, this we need to solve numerically, and few solutions of these I am providing here. But we will be having infinite number of solutions. So, first 3 solutions are these. And once we obtain this, because we know alpha and omega NF are related, so natural frequency can be obtained. But you can able to appreciate that with the addition of the mass itself, the frequency equation which was earlier simpler, now it has become a transcendental equation, and solution of those roots are not easy now. So, in the present lecture, we introduce the continuous system approach for torsional vibration. This particular system is most accurately we can able to model the system, we can able to get the natural frequency and eigenfunction, but the difficulty is for very simple boundary condition we can able to get the solutions. For more complex conditions we need to go for approximate solutions, and in the subsequent class we will choose finite element method for solution of such system, in which will be, because we know that finite element method is having flexibility in incorporating more complex boundary conditions. So, that particular method will be exploring in 2 lectures. In this continuous system approach, as we have seen that we solve the system equations as a whole. In the subsequent lecture, we will see when we will be using the finite element method. In that particular method, we break the system in various small segments that we call it as element, and we obtain the elemental equation. And once we obtain the elemental equation, then we obtain the system equation by assembling such elemental equations. and then finally we apply the boundary condition to get the governing equation for the whole system. So, that particular method we will see in the subsequent lecture.